All right, we're going to talk about heat transfer. This is a topical outline of what we're going to do. We're going to talk about how heat, which is energy, moves. We're going to talk about heat transfer coefficient, U values, HTMs, heat transfer multipliers, and we're going to define sensible and latent heat. We're going to tell you what to measure. Walls, gross, then net. We'll talk about that. Partitions, knee walls, floors, slab, elevated, below grade floors, ceilings and roof combinations, windows, glazing, fenestration, whatever you want to call it, and direction become important. Doors, people and appliances, all those things we're going to talk about. We're going to give you some formulas for area and volume because a lot of houses have turrets now. A lot of them have vaulted ceilings, so you have to understand prisms. Okay? Zoning. What constitutes a zone? We'll do a little thing in that. It's not going to be any detail on zoning. This is not a zoning CD, but we're going to cover some stuff that's important, some considerations that should be important to you. All right? So if somebody will hit the magic start button, we will get going. Thank you. Cold can be defined as the lack of heat. Cold can be defined as the lack of heat. Cold starts at minus 459.6 and below. That's about the temperature of outer space. It's very close to absolute zero. Minus 459.6 Fahrenheit is absolute zero. At that point in time, all molecular movement ceases. If you were to be able to stay alive in a minus 459.6 environment, let's say a minus 459 environment, the blood rushing through your veins or barely moving through your veins would rub up against the walls of the vein, and that's friction, and that creates heat. Now, I wouldn't want to defrost frozen pizza with that amount of heat, but it's still heat, and technically we have to count it. The same way that minus 20 degree air, 20 degrees above zero air, and a heat pump can extract heat from 20 degree air. All we need is a fluid, a media, a refrigerant that can drop its condensing temperature 10 or 15 degrees below 20, and if we can do that, we can absorb heat from that because hot goes to cold. You'll see that in the next slide. Cold doesn't start until you get to minus 459.6. So everything we deal with, heating, cooling in our world, is heat movement. So when I talk about the heat moving in a cooling situation, I'm talking about hot air going to cold air. All right? Everything else is heat. Anything above this temperature is heat. Heat is energy. Okay? Heat is energy. They are the same thing. Remember, cold is lack of heat, and therefore lack of energy. No molecular movement. The cells in your body, the nucleus and all the particles of the cell can't move, and they can't absorb oxygen. They can't pass blood along. They are dead from the lack of energy, the lack of heat that's involved. Okay? You have to, if you want to understand how heat moves, you have to stop thinking about heat in terms of hot air. Hot air rises, that's fine, but heat does not. Heat moves downhill relative to temperature. That's where heat loss and heat gain terms come from. In cooling, we talk about gaining heat because the hot air outside goes to something with less heat, less energy inside. It's colder inside, so it's a heat gain. The heat loss is in the wintertime because it's hopefully warmer inside than it is outside. And again, the same direction. Hot's going to go to cold. It will never go the opposite way. So if your parents yelled at you like mine did when you were a kid, and they said, hey, close the door in the wintertime, you're letting the cold air in. They're wrong. Hunt them down, correct them. They're wrong. The hot air leaves. The cold air does not come in. All right? Just teasing. Be kind to your parents. So heat energy moves in one direction only, from something with more heat to something with less heat, always. The greater the temperature difference, the greater the quantity of heat that will flow. You need a good degree and a half or so before you really appreciate any movement. Most people can't perceive, except my wife. She can tell when there's 1/10 of a degree temperature difference in a room, but most people can't sense anything below 3 degrees. It's difficult, depending on the person. Women, the blood is closer to the surface, and they might be a little more sensitive, but you really need an accurate thermometer to find out otherwise. Hot air rises. Okay? Hot air rises, but heat flows downhill relative to temperature. Why is this important? Because if you're going to supply heat from overhead, and you have not a high velocity, a halfway decent velocity, and you can penetrate that room with that temperature, the heat from the high point will flow to the cold point. Not the hot air. The hot air is going to rise up around the ceiling. You're going to get a convection current. All right, the cold air is going to fall. In a situation like this in the wintertime, 0 degrees, you're going to have probably 62, 63 degree floor all winter long. The temperature of the air coming in from the ceiling could be 100, 110, 120, depending on how old the furnace is. That 100 degrees will go to the 60. All right? My grandmother, I'll give you an example. God bless her. She was 84 when she passed, and for about 10 years prior to that, she lived in a retirement community in Long Branch, New Jersey, who has very often, especially back then, 0 degree winters. It was across the street from the ocean, right on the shore, so it had all the wind and everything else. And this retirement community she lived in, the homes were made out of concrete slab on grade, and back then they didn't use any insulation at the concrete slab. All right, I checked their floor temperatures. They were always in the low 60s all year long, and the heat was supplied by electric ceiling panels. You couldn't see them, of course. They were behind the sheetrock, but they were electric heat. She could make that house any temperature she wanted, and she often did. I hated going over there in the winter because you couldn't breathe. You know how the old folks like it 80 degrees and they want 90% relative humidity. The wallpaper used to peel off the walls in that house, but that's what the old folks do. So I want you to understand this. Don't think, oh, I can't bring I'm in an attic and, you know, I got to bust up the frame to get low in the outside wall. It's not necessarily a requirement, especially when you're on a second floor. Don't worry about supplying heat from overhead in a cold climate, because you got the whole downstairs heating situation that's rising to the upstairs. By convection, the hot air will rise and warm those second floor floors on the way up. Heating from overhead in a second floor is no sweat, but you can also do it on a cold floor, elevated or slab, either one. All right, you have to exercise caution here. This is not carte blanche, but it can be done. We do it often. Most people in the northern climates understand that. Sure, it's better if you can supply heat low because it penetrates the room a little better. It's better if you supply cooling from overhead because you know the cold air is going to drop and the hot air is going to rise and all that good stuff. But is it absolutely essential? No, it's not. You can do it either way you want to. And again, I'm not telling you something from I read in a book. It's something I've done for the last 40 years. I've read everything there is to read about it. I've tried everything there is to try about it. I've done thousands of houses, involved with track work at one time, tens of thousands of houses, and I've made enough changes in the design work that we were supplying to be able to see what affects what. So it was a very good education for me. Anyway, heat moves in 3 ways: convection, conduction, radiation. You've heard this song and dance before. The thing most textbooks will lead you to believe is that it only works in one way or the other. The fact is that if heat is moving, all 3 are in play at the same time. It's almost impossible to have either only convection, only conduction, or only radiation. Convection happens only in fluids, and understand that water and air are both considered fluids. because in either water or air, the hotter fluid will rise to the top, the colder will drop to the bottom and displace the warmer. All right? That's a convection current. Conduction, heat moves through a material. Get a new guy in a job, right out from flipping burgers in McDonald's, and you're going to make him an installer in 2 weeks, and you hand him a 3/4 inch piece of pipe, copper, you have him hold it while you sweat a fitting on the end. Well, if he doesn't have gloves on, he's going to drop it in about 30 seconds. That's conduction. The heat moves through the material. Radiation. Radiation, the best example of this is the sun heating the earth. The sun, the surface of the sun, is average about 10,000 degrees Fahrenheit. But it travels through minus 450 some degree temperature, doesn't warm up space. Outer space isn't getting any warmer because our sun and a billion other stars are out there at the same temperature or hotter. It travels through space without warming the objects, without warming the air, and it warms the objects up. Just like this cat sitting in front of the fireplace, or you standing in front of a fireplace. You know when you turn away from the direct radiation of that fireplace, you don't feel the heat intensity anymore. All right, that's radiation. If you've walked through a warehouse with radiant heaters, 40 degrees, 50 degrees in a warehouse, but walk up to a box or a table in a warehouse and put your hand on it, if they're using radiant heat, that object is warm. And that's how radiant heat works. It heats up the object just like the sun heats up the earth, and then that heat radiates back out to space again, which is cold, because hot always goes to cold, and on the way out it warms up the air. The same with radiant heat in a warehouse. Heat up the objects, they radiate heat to the air and temper the air. All right. The problem with what we're doing today with refrigerants and other devices, CO2, we're not allowing the heat to get back out again. We're creating global warming. That's a whole nother issue. Okay, infrared thermography. This is one way you can actually see the conduction of heat through materials, through buildings, through your feet, through your skin. Your core temperature is about 98.6, hopefully, but the surface temperature of your body is about 85, 83, depending, degrees. So it's considerably different. But you can see the heat emission from that as a result of this thermography. This is a technology that's available to us now. In fact, someone told me recently, I haven't had a chance to investigate it, but one of our major equipment manufacturers, and I don't mean heating and air conditioning, I'm talking about tool manufacturer, if you will, like Amprobe, and I don't know who it is, I can't remember, has made a infrared camera available. Now remember, you don't take pictures with an infrared camera, you observe. You will see him when you point it at a building, you'll see the heat loss through the building represented by color. Of course, the red is more intense than the darker colors, that kind of thing. So you can use it for a lot of, I would love to have one for my own house just so I can see where my heat loss is the greatest. Because wherever the heat loss is the greatest, that's where the heat gain is probably going to be the greatest as well. You can see the difference in good window, bad window, just looking at these slides. The bad news is, the good news is the technology is available. The bad news is a cheap infrared camera goes for about 8 or 10 grand. So hang on for a while. I'm sure, like all things, it will reduce in price. Hopefully not in intensity. So let's talk about some things here. This gives me an opportunity to talk about density and volume and those kind of things. So what do you think is heavier, a pound of bricks or a pound of cotton? Well, obviously a pound is a pound, but it does give me an opportunity to talk about density. And density is defined as pounds per cubic foot of a material. Take a cubic foot of it, fill that cubic foot with material, and weigh it, okay? If you were to take a cubic foot bucket, that's 12 inches by 12 inches by 12 inches, and you put